Hello, this video is for Algebra 1, Lesson 4-4. It is titled Graphing Functions. The objectives for this lesson is to graph functions given a limited domain and also graph functions given a domain of all real numbers. So who uses this? Well, scientists can use a function to make conclusions about rising sea level. Sea level is rising at an approximate rate of 2.5 millimeters per year. If this rate continues, the function y equals 2.5x can describe how many millimeters sea level, using y to represent sea level, will rise in the next x number of years. So in this particular equation, y represents the sea level and the x value represents the number of years. One way to understand functions, such as the one above, is to graph them. You can graph a function by finding ordered pairs that satisfy the function. And you can see over here on the right, we have the current Florida coastline. Looks like that. And now this here shows that a possible Florida coastline could look like in 2,400 years from now, which is a really long time. I think Disneyland's going to be all right. It's right there in about Orlando. So it looks like 2,400 years, Disneyland will still be around. Or is it Disney World? I always mix the two up. One's in California, the other one's in Florida. So graph solutions given a domain. Remember, domain is all of our x values. It's the inputs. And a helpful hint is sometimes solving for y first makes it easier to substitute values of x and find ordered pairs. Remember, an ordered pair is an x value and a y value separated by a comma and contained inside of parentheses. We can see some of those down here in our table. X value, y value, separated by a comma and contained inside of parentheses. To review solving for a variable, see lesson 2-5. So here's our equation here of negative x plus 2y equals 6. We're given the domain of negative 4, negative 2, 0, and 2. So those are going to be our inputs into our function. Step 1 is to solve for y, since you were given values of the domain, or that is to say your x values. So let's go ahead and do that first. Here we're going to go ahead and add an x to each side. That'll get rid of the x over here on the left, and now it's going to put it over on the right. The negative x and positive x cancel each other, leaving us just 2y on the left, and then a positive 6 and a positive x. We get x plus 6. Now the 2 is tied to the y through multiplication, so we're going to divide by 2. That leaves us just y on the left, and then dividing the right side by 2 gives us x plus 6 over 2. And we could split that apart into x over 2 plus 6 over 2. And then finally, let's go ahead and take the 6 over 2, simplify that down to 3. So we've rewritten our function here and solve for y. So we can go ahead and make that our function rule in the table. So step 2 is to substitute the given values of the domain for x and find values of y. So in the first column, I have all my x values. These are the domain. We get those numbers up here from the top, negative 4, negative 2, 0, and 2, negative 4, negative 2, 0, and 2. In the center column is where we're going to put our function rule. So we're going to write our function each time, y equals 1/2, then whatever x is, plus 3. And then we're going to have our solution to that, working each of those out. You can see all the way down through all 4 of these rows here that the domain has been plugged in, or that is to say the input are the x values. And all of them have been solved. We see the solutions here in blue. So our x values are in green. Our solutions, the outputs, the y values, they are in blue. So this is where we get our ordered pair that show up in the third column. Input of negative 4, output of 1. Here we have negative 4, 1. Input negative 2, output positive 2. So we get negative 2, 2. Input of 0 and output of 3. So we have the ordered pair 0, 3. And then finally an input of 2 and an output of 4, our last ordered pair of 2, 4. Step 3 says to graph the ordered pairs. So let's go ahead and graph these. First, our ordered pair negative 4, 1. So x is negative 4. Y it has a value of 1. So this is where we would plot that point. Then we have an input of negative 2 and an output of 2. So look for negative 2, 2. X has a negative value of negative 2 right here. Y has a value of positive 2 here. So this plots that point where x is 0 and y is 3. So x is 0, y is 3. So that's that point there. And then finally 2, 4, where x is 2 and y is 4 gives us this point right here. So we end up with a graph of the function and by plugging in our domains right there. Okay, so let's go ahead and take a look at the next slide here. Graph each function for this given domain. So our function is the f of x equals the absolute value of x. Now remember, did they give us f of x on that previous one? Take a peek there. And this one here, no, we solved it for y, and we ended up with y equals, and then our function rule here. Well, remember that f of x is pretty much the same thing as y. F of x and y are interchangeable with one another. So this is like saying y equals the absolute value of x. Our domain is -2, -1, 0, +1, and +2. So step 1, use the given values of the domain to find the values of the function of x, or f of x, that is to say, also known as our y values, right? So instead of having x, y, we have x and the f of x, which y is a function of x. That's why they're interchangeable like that. So in our table, in the first column, are all of our x values. That is to say the domain. Notice those are in green. And we're going to find the value of y, or that is the function of x, and that's going to be in blue. Again, we have the function rule at each of these rows in the second column. We're plugging in our domains into the absolute value and then getting their solutions. So when our input of -2 produces output of 2, input -1 produces output of +1, and input of 0 produces an output of 0, input of 1 equals or produces an output of 1, and an input of 2 produces an output of 2. A lot of inputs, outputs, and produces there. So graph 2, or step 2, is to graph the ordered pairs. So let's go with -2, 2. So -2, +2, that's that point there. -1, +1, -1, +1, so that's that point there. 0, 0, well, that's right at the origin, right? Where x is 0 and y is 0, we call that the origin. So we're going to plot a point at the origin. 1, 1, x1, y1, so that's that point there. And then finally, 2, 2, x is 2, y is 2, that's this point here. So we have graphed all the ordered pairs on our graph. If the domain of a function is all real numbers, any number can be used as an input value. This process will produce an infinite number of ordered pairs that satisfy the function. Therefore, arrowheads are drawn at both ends of a smooth line or curve to represent the infinite number of ordered pairs. If a domain is not given, assume that the domain is all real numbers. So if they don't tell us this is the domain, then we'll assume that we can plug in any real number as an x value to get back another real number, which would be our y values. Graphing functions using a domain of all real numbers. Step 1, use the function to generate ordered pairs by choosing several values for x. We've done that in the last couple examples. Step 2, we then plotted each point to see the pattern of the graph. And then step 3, connect the points with a line or smooth curve. We've not done that yet on this one. We could, and we'll see on the upcoming ones, but we could connect all of those by putting a line through them, and we could see that it would look something like that. And what they're saying is that you would have to put arrows on the end, or arrowheads is what they call them, on the end to represent that even the numbers we don't see on the graph, that they too would also be solutions that would satisfy that particular function. Looking at the next slide, step or example 2, graph functions and graph each function. So 2x plus 1 equals y. We're going to choose several values of x and generate ordered pairs. We don't necessarily have to solve for y. It's not on the right side, it is on the left, but hey, we'll be okay with that. We're going to go ahead and make that center column there our function rule column. First column is going to be all of our domain, or all of our x values. Notice they don't give us a domain. So since the graph is pretty much, we can see the origin there, so we know numbers like 1, 2, 3, and 4 are going to be there for both the x values and the y values. So those are the numbers that we want to choose as inputs to go ahead and plug in to our function rule here in order to generate values of y. So let's go ahead and plug each of these in. So -3 gets plugged in for the value of x. Solve it, it's -5, so it produces the ordered pair of -3, -5. -3 is the input, -3 is the output. Let's kind of skip around here. -1 is an input, -1 is the output. If we plug in a value of 1, we get back a value of 3. If we have an input of 3, we have an output of 7, and we can see the ordered pair 3, 7. So all of these ordered pairs here match up with the green numbers, which are x values, and then the blue numbers, which is the result of evaluating that function rule, and that gives us all of our outputs. We get also, notice this time it's y, and other times it's f of x. Remember, f of x and y, two different things. They're the same thing, they're just interchangeable. Y is a function of x. So step 2 is to plot enough points to see a pattern. So notice that we've got 1, 2, 3, 4, 5 points. And it looks like we've got, what, about 7 different rows here. We calculated up 7 different inputs, but only 5 points. So if we kind of start from the middle at 0, we'd have 0, 1. There's 0. There's y value of 1. We plot that. What about 1, 3? Yep, that's here. 1, 3. That point there. What about 2, 5? 2, 5. We see that point there. And how about 3, 7? Well, x has a value of 3. That is on the graph, but 7 is going to be up here. We can't see it. So at that point, we're not going to plot that point because it's not on the graph. Going the other way, -1, -1, -1, -1. So that's that point there. -2, -3, -2. Oh, here we go, -2, -3. So that's that point there. And again, we have another point that's not going to show up on the graph. If we have an input of 3 and an output of -5, input of -3, and then the output of -5 is going to be down here. It's not on the graph, so we're not going to plot that point. So in step 3, the ordered pairs appear to form a line. You can see the line's been drawn through it. Draw a line through all the points to show that all the ordered pairs that satisfy the function. Draw arrowheads on both ends of the line. The arrows at the end of the line let us know that even beyond what's off of the graph that we can't see, that those points are also solutions to our graph. Also, I want to demonstrate and talk about how all the area in between the points on the line, that they too are possible solutions to this function of 2x plus 1 equals y. For example, let's go ahead and look at what if x were 1/2. What if we plugged in 1/2? And that matches up right about here at 2, right? Well, if we plugged in a value of 2 right there, or 1/2, we plugged in a value of 1/2, what is 1/2 of 2? 2 times 1/2, well, that's 1, right? 1 plus 1 is 2. 1 plus 1 equals 2, so we would expect a y value of 2. And exactly, that's sure enough what we get there. So key thing to remember is that not just the points that we've graphed, but also all of the points in between those points that are on the line of that graph, that they too are possible solutions to that function. Looking at the next slide, graph each function, and on this one here we have y equals x squared. Choose several values of x and generate ordered pairs. Well, we're using this graph here, and we can see that our x values that we have here anywhere from -5 to +5, right? So we want to pick numbers that are in between there. So we'll grab -3, -2, -1, 0, 1, and 2. If we plug all of those into this function rule here, we've just substituted in the value of x each time, evaluated it, and came up with each of those answers. Remember the answers in blue? Those are our y values. The numbers in green, those are x values. So we get all 6 of these ordered pairs here. Start plotting them. -3, 9. Here's -3, here's 9. So that's that point. -2, -4, -2, or +4, excuse me, +4. -1, 1. So -1, +1, that's that point there. 0, 0, that's the origin. 1, 1, right there. And then 2, 4, right there. Now it looks like we could also have one right up here at, notice where that looks like it's on the graph there as well. And what is that? That's 3 and 9. Well, 3 squared, if we plugged in a 3 there, we would indeed get 9. So we realize that there's another example. Looking for my eraser here. Oh, there it is. It's another example of how the line represents all possible solutions. So let's read on and see what step 3 says. The ordered pairs appear to form an almost U-shaped graph. It's called a parabola. Draw a smooth curve through the points to show all the ordered pairs that satisfy the function. Draw arrowheads on the ends of the curve. They've done so there and there. Now we can check if the graph is correct. Any point out will satisfy the function. Choose an ordered pair on the graph that is not on your table, such as 3, 9. Check whether it satisfies the function y equals x squared. And that's what I did. That's even the point. See, great minds think alike. And I hadn't even really read that ahead of time. But yeah, if I plug in a 3, square it, it produces 9. So that point would be on the graph as well. Recall that in real-world situations, you may have to limit the domain to make answers reasonable. For example, quantities such as time, distance, and number of people can be represented using only non-negative values, that is to say positive values. You can't have a negative 6 hours, a negative 12 feet, or a negative 23 people, right? All those in real-life situations, we would use positive numbers, that is to say non-negative values. When both the domain and the range are limited to non-negative values, or to say positive numbers, the function is graphed only in quadrant 1. In quadrant 1, whenever you look at a coordinated plane, you have the y-axis, the x-axis going across, the y-axis going up and down, and it produces 4 sections. The one in the upper right-hand corner, like over here, this is known as quadrant 1, and the quadrants go counterclockwise. This will be quadrant 1, and if the rest of the graph were here, quadrant 2, lower left corner, quadrant 3, lower right corner, quadrant 4. So let's go ahead and do some problem solving with example 4. And this looks like it is going to be our rising water levels that are going to be flooding Florida in the next 2,400 years. The function y equals 2.5x describes how many millimeters sea level, represented with y, rises after x years. So years is the x value. Graph the function. Use the graph to estimate how many millimeters sea level will rise in 3.5 years. So understand the problem. The answer is a graph that can be used to find the value of y when x is 3.5. That is 3.5 years. We get that number from the question of how high will the water rise in 3.5 years. List the important information. The function y equals 2.5x describes how many millimeters that the sea level rises. Let's make a plan. Let's think. What values should I use to graph the function? Both the number of the years sea level has risen and the distance sea level rises cannot be negative, so it's all going to be there in quadrant 1. Let's see. Use only non-negative values for both domain and the range. The graph will be graphed in quadrant 1, as we said. Also, all graphs should have a title to them. So you should have a title above a graph to let you know what it's about if it's a real world situation. And this one here, we have a title, sea level. Now, we have to determine what should the x-axis be and what should the y-axis be. Well, in this case, the sea level rising is a function of years. So time in years is going to be the independent variable because time is what's causing the sea level to rise. So as time increases, the sea level increases as well. So our independent variable is going to be the x-axis. Time is affecting the sea level. So the one that's getting affected is the dependent variable. That's going to be the y-axis. So that's why we have time is on the x-axis and y, or the sea level, is on the y-axis. So we create a graph, or table here. We have a table, and we're going to go from a table to a graph. So first column, again, our x values, that is to say our domain or our inputs. Second column, function rule, where we're going to rewrite the rule, and each time we're going to plug in the value of our input, that is to say our x value. We'll solve each of them, giving us the blue numbers, which are the answers to each of those, or that is to say our outputs, also known as our range. And then we can take the x and the y value and create ordered pairs. It's been, all the work's been done for us here. So we have 0, 0, that's the origin. 1, 2.5, where x is 1 and y is 2.5 right there. 2, 5, here's 2, there's 5, so there's 2, 5. 3, 7.5, x is 3, 7.5 for y, that's there. And it looks like whenever we're at 4, we have to be at 10, and oh, just barely on the graph there. I guess technically we could squeeze a dot in right there and say, yep, we got that one there. So let's use the graph to estimate the y value when x is 3.5. The sea level rise about, oh, that's the answer there. So let's go ahead and do that. Let's go ahead and find, I'm going to change colors here. I don't want to use blue. Maybe green. Yeah, we'll use green. So whenever x is 3.5, so we go along the x-axis here and we find 3.5. It's right in between the 3 and the 4. I think I got kind of close there. Go up to where it touches the graph, and it touches right there. And so then we go over and see, well, what would the y value be for that corresponding spot? And it looks like it's going to be right around 8.5 or so. But let's go ahead and read on. So sea level rise is about 8.75 meters in 3.5 years. So looking back, as the number of years increases, the sea level also increases. That's why the graph's going up. If you see the graph's going uphill from the left to the right, we say as whatever x is increases, then whatever y is, it increases as well, because both numbers are increasing. So as years increase, the sea level increases. So the graph is reasonable. When x is between 3 and 4, right there between 3 and 4, y is between 7.5 and 10. So we see it's between, well, this dot here, 7.5 and 10. Since 3.5 is between 3 and 4, or that is, say, like halfway in between, it's reasonable to estimate that y would be 8.75 whenever x is 3.5. So just eyeballing it, we said it was like 8.5. Turns out to be it's 8.75. Pretty close, right? So our guided practice for this one, graph each function for the given domain. Well, let's go ahead and pick one of them out. Let's go ahead and just do number 1 real quick. And this is 3x minus y, and that's supposed to equal 1. And our domain should be the set of -3, -1, 0, and 4. So first thing we need to do, let's solve for y, right? So let's go ahead and let's add a y to each side. If we add a y to each side plus y, we would end up with those y's would cancel, and we get 3x and equals, and then we have a positive y, and we have a positive 1. Now let's go ahead and subtract 1 from each side, and that would give us 3x minus 1 equals, the 1's canceled, and we get y. Now I'm going to go ahead and flip that around to y equals 3x plus 1. And now this is all my work here. Actually, I'll just go ahead, instead of erasing it, I'm going to go ahead and grab all this here, and we'll move it over there so we don't forget where we got the function here of y equals 3x plus 1. Let's go ahead and substitute some values in. If we put in an x value here of -3, and our function is going to be, let's make a table here. Our function is 3x plus 1. Now I'm going to go ahead and put that y on the other side, right? And then our answer over here is going to be our y values. So 3 times -3, and then we're going to have to add 1. So 3 times -3 is -9, plus 1, what is that, -8, correct? -9 plus 1, yep, good to go. Plug in -3, we get -8. What about if we put in a -1? So 3 times -1, add 1, well, that's -3, plus 1, it's going to be what, -2? And if we have 0, well, this was a fun one, makes it kind of easy, because we know that this is going to equal 0, so we're just going to get 1. And finally, I'm going to squeeze in a 4 right here. 3 times 4 plus 1. All I'm doing is just substituting in my x value into the function rule. 3 times 4 is 12, plus 1 is 13. Now, I'm not sure if 13 is going to show up on this, right? Looks like it goes out about 10 spaces or 10 units on there. So I'm going to use one for each one, so we might not get them all on there. Let's go ahead. X is -3. 1, 2, 3. Here's -3 right there. And I'm looking for -8. 1, 2, 3, 4, 5, 6, 7, 8. So that's 1 point right there. And X is -1. Oh, if you were hollering at me, that's +3, that's +3, you would definitely be correct. So 1, 2, -3 is right here. And then I want to go to -8. 1, 2, 3, 4, 5, 6, 7, 8. Yep, it's 10. I could have just counted from the bottom, right? And where I have -1 right there, that's going to be matched up with -2. So that's right here. And I know because it's x to the first power, this should form a straight line. Where x is 0, y is 1. So that would be there. And where x is 4, 1, 2, 3, 4, I should get 13. Well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 13 is going to be up there someplace, so I can't really graph it. But if I go ahead and put a line through these here, I'm going to drag this up, and I'm looking to make sure that that goes through all those points just right. And I'm going to make it a little bit longer so I can find that +13 where that would be. About like that. And now if I go ahead and look 4 up here, 13 would be like right about there. All right. I'm going to go ahead and erase all of this. And we'll go ahead and pick another one. Let's go to example 2. Which one looks good here? It says graph each function. Let's do x plus y equals 0. That one ought to be interesting. Let's do number 7. And I am in red because I was still writing on my graph there. Let's do number 7. We're doing x plus y equals 0. What if we solve for y? Let's go ahead and subtract an x from each side. Add a -x there. And so now we end up with a positive y. And 0 minus x, well, that's going to be a -x, right? So let's go ahead and move this over to the side here. Let's grab this here, and that is our function. You might be wondering, well, what's that leave us with? That looks a little awkward, don't it? So, but let's try it. Let's go ahead and whatever x is. So let's just pick some, we got some positive numbers and negative numbers here. Let's try -3. So we're going to plug in a value -3, and this is going to be our x inputs, right? There's our x inputs. I should move. Let's see. Let's move this over to the side. There we go. That is our function that we're dealing with there. This is going to be our inputs here. Our function rule says that y equals -x, or I'm going to flip that around. Let's go back a little bit. Let's just flip it around to say -x equals y. Same difference, right? And then let's have our outputs. These are going to be our outputs here. So let's plug in a -3. So -3, and notice how it's just the x. The negative sign is still out in front of that, okay? And let's plug in, say, 0, right? So -0 equals something. Let's plug in 2, +2, negative, opposite, -2, and let's plug in 5. We'll try that. Notice all I'm doing is wherever x is, I'm just plugging it in and substituting. So you could think of this as -1 times -3 to get a +3, or you could think of it as the opposite of -3, which is +3. What's the opposite of 0? Well, that's just 0. What's the opposite of 2? -2. The opposite of 5? -5. So there's our outputs. So our ordered pairs. Put in a -3, we get back a +3. Put in a 0, we get back a 0. Put in a 2, we get back a -2. And if we put in a -5, or put in +5, close that off, put in +5, we get back -5. Let's go ahead and plot those on the number line. -3, 3, so there's -3, it's going to be +3, that's right here. 0, 0's right here. +2, -2, it's going to be right there. And 5, -5. 2, 3, 4, 5, Negative 5 should be right here. Go ahead and put a line through it. And I know that this is just like that. Because here's a fun part. If you ever see y equals x, and I'm writing with a line there. If you ever see y equals x, that looks like this. It's a diagonal line from the back, silly line. Thank you. It is a diagonal line that goes from corner to corner, and it passes right through the origin. That is the function of y equals x, is right there. That's that one. Now, and I'm going to change over to white real quick, y equals negative x is this function right there. Undo. Trying to be sneaky and draw with lines. I just so happen to know that y, x, negative, equal, all that are straight lines, so I can be kind of tricky and try to draw with or write with the line tool. So at any rate, y equals x goes uphill from left to right. Y equals negative x is just the opposite. It's a downhill diagonal through the other way. Wasn't planning on teaching that. I just so happened to come across that, so I figured I'd go ahead and use that. Looking at number 11, use a graph of the function to find the value of 2. Yeah, we'll go ahead and do that. I'm going to go ahead and erase all this, and then we'll do that. All right, so we're good to go. And let's go ahead and do f of x. That's the same as y, right? So if you want, you could write this as f of x equals 1/2 x minus 2, or the same difference would be y equals 1/2 x minus 2. So let's go ahead, and they want to know whenever it's 2. So I'm not going to use 2 for it because the idea is to predict, well, to use a graph. They want us to use a graph. So I'm going to go ahead and I'm not going to use this value of 2 whenever I create my table because I'm going to use the graph to show what it would be. So if you're thinking just plug in the 2, there's a reason I'm not doing that. So our x values, and we're going to have a column for those, and our function rule, and then this is going to be our y values here. We'll actually probably put our ordered pairs over there. Our rule is that 1/2 x minus 2 equals y. So let's pick some numbers. Let's go ahead and pick -3, -2, 0, 1, and I told you I wasn't going to pick 2, so I'll go ahead and pick 3. So well, that's not going to be fun. I'm going to cheat a little bit here. I just realized something that I don't want to do. Let me get my eraser, change it kind of small so I can do some erasing there. I don't want to use odd numbers because I'm multiplying times 1/2, and I don't want to work with 0.5s. So let's try 4 and 4 there. And that's a -4. So 1/2 times 4 minus 2 equals, well, 1/2 of -4, right, is -2. -2 minus 2 is what? -4, right? 1/2 -4 is -2. -2 minus 2, yep, there we go. Then I got 1/2, trying to squeeze this in here, times -2 minus 2. 1/2 of -2 is -1. -1 minus 2 is going to be -3. 1/2 of 0 minus 2. Well, 1/2 of 0 is 0. Subtract 2, I get -2. I don't want 1. Let's see. Can I try it? 1/2 of 1 minus 2 equals, well, 1/2 of 1 is 1/2, right? Minus 2 would be a -1.5. Okay, and then I have 1/2 of 4 and minus 2. 1/2 of 4 is 2. 2 minus 2 is 0. So my ordered pairs are -4, -4. Don't forget the parentheses. -2, -3, and 0, -2, 1, and -1.5. I'm going to wish I didn't use that one. And if I plug in a 4, I get a 0. So let's plot those ordered pairs. -4, -4, -4. That's 1, 2, 3, -4, Negative 4 should be right there. Negative 2, negative 3, negative 2, negative 3, 0, negative 2, and 1, negative 1.5. So that'd be right about there. Sneak that one in. And we're 4. X is 4. 1, 2, 3, 4. Y is 0. So I can then go ahead, run a line between these from that one right there, right through. Yeah, there we go. Because I can peek over that. I know the slope is 1/2. So it should look like that. I'm cheating because I know other stuff that we'll learn in the future. And now the question becomes, what if x were 2? So let's find 2. 1, 2, right there. That matches up with right here. So if x were 2, where's the highlighter? If x were 2, it should be negative 1. Let's see, would that work? If we plug in 1/2 of negative 1 minus 2, 1/2 of negative 1 is a negative, oh, that's not negative 1. That's a positive 1. What is it? I'm supposed to be plugging in 2. Silly me. I'm getting all confused. So 1/2 of 2, there we go, minus 2. So 1/2 of 2 is what? 1. 1 minus 2 equals negative 1. Sure enough, I would end up right there at negative 1. All right, so that's everything I got for you for Algebra, Lesson 4-4, Graphing Functions. Now, go level up your learning.